Hi, folks. I wanted to take a minute to explain the concepts that are at the foundation of the KERI ecosystem that some of you may have felt were a little bit mysterious. SADs and SEDs and ACDCs. There are other explanations of these out there, but I'm going to try to explain them from a perspective that may be helpful to people who already understand verifiable credentials and DIDs, and try to contrast specifically these technologies with ones that you may have already encountered and explain why they're interesting. So, let's go ahead and get started. First of all, let's talk a little bit about the problem of tamper-evident documents. We've had this problem ever since we've had the internet. It becomes important to prove that you're looking at the right version of data. And this slide shows a little screenshot from a download page that I went to recently. I was downloading some video editing software, and at the bottom of the download section was a comment saying, here's the checksums that you can use to verify that the download you're getting is the right one, hasn't been modified by a hacker or something like that. This is standard practice in many downloads. It's used to verify packages. The same technique is used to verify packages when you install on Linux, for example, install a deb file or an RPM. It's used by BitTorrent to prove that the big files you're downloading over peer-to-peer file sharing on the internet are actually the right content and haven't been modified. And the general pattern here, the author publishes the file and publishes the hash of the file, and then the reader checks the hash and knows that the file they've got is the same one the author intended. So hopefully that feels comfortable to you as a concept. Now, there's several challenges with this mechanism. I listed 3 here. The first one is that the files and their hashes can be separated from one another. If you encounter the file, but you don't encounter the hash, you don't know whether a hash for this file exists, and you don't know what the author's intention with respect to tamper evidence might be. Files can evolve, and we say that this is the final version of something. This is a document we've written and it's now final, only to discover a minute later that we've got a typo that we have to fix. But there's other kinds of changing that happens that's a little bit less obvious, like the idea that we download some JSON and then open it in a IDE, and the IDE helpfully reformats the JSON to make it look prettier with indentation and so forth. We may not realize that the file has changed. In programming, it's common for the carriage return line feeds on Windows to be changed into pure line feeds on a Mac and back and forth. It's also not unusual to add a carriage return at the end of a carriage return line feed at the end of a file that doesn't have one. Those kinds of simple changes can create problems when you're trying to validate that a file hasn't changed and you don't realize that an innocent change happened. And that brings us to problem 3, which is that we'd like to be able to ignore differences that aren't significant. And all of those are not possible with the simple form of hashing that is familiar to us. So this brings me to the topic of SADs and SEDs. to explain this, let me start with the concept of a document. Now, this document could be something that's not human readable. It doesn't have to be, a word processor type of a document. It could really be anything, digital, music, video, photo, compiled software, whatever. But I'm just going to represent it as a document right here. And let's just imagine that we would like to apply our data integrity technique of hashing the document so that we know that the document has the right stuff and so that any tampering becomes evident to us. So what SADs and SEDs do is they say, let's look at that document and we want to hash all of this, except they make a room in the document for a particular region that isn't going to be hashed. And they allocate semantically to that region the role of holding the hash of the document itself. So basically you have the yellow portion of the document here is what needs to be hashed, and the blue portion of the document is where the hash goes inside the document itself. And that causes, that leads us to the names. So the SAD, self-addressing data, is the yellow portion, and the SED, the identifier for the self-addressing data, self-addressing identifier, is the blue portion. So the combination of a SAD and a SED is a whole document. The document as a whole is known as a SAD when it has the SED in it. If the SED is missing, then it is potentially self-addressing data, but because the SED is missing, it's not yet self-addressing. So it's the combination of the two that makes a complete SAD. And what's interesting about this is that you could, when you're referring to the self-addressing data, you could provide the data itself, say, here's the data I'm talking about. But if somebody already has a copy of the data or has a way to get a copy of the data, you can simply provide the data's SED, and then when they go get the data, they know they have exactly the thing that you were referring to. So a SED is essentially like a hyperlink to the data that it identifies. And when you get the data that it identifies, you will see the SED inside the data. Now, let's take this notion about documents and apply it to the world of serialized data a little bit and talk a little bit about CESR. CESR is a serialization strategy, and it has several unique properties. The headline here is that it understands binary and text transformations of the same data. It also understands cryptographic primitives, and it understands the concept of SADs and SEDs. So what this allows is that you can freely mix binary versions of data, such as you'd get with CBOR or MessagePack, and text representations of data, such as you'd get with JSON. And because CESR understands that, like CBOR is just a transformation of JSON and vice versa, MessagePack is just a transformation of CBOR or JSON, because it understands that these are alternate representations of the same thing, the way that it calculates a hash doesn't depend on which representation you're using. It depends on what the meaning of the underlying data is. So that means that you can freely mix these representations, but the hash remains stable. And you get the terseness of binary, but the human friendliness of text. It also means that unimportant differences in JSON, like adding carriage return line feeds and white space and stuff like that, don't change your hashes. CESR also makes hashes, cryptographic hashes, and cryptographic keys first-class data types. It knows when it's looking at something that is cryptographic in nature. So the workarounds that we have in JSON where, oh, you want to put a, let's say, a hash in a JSON file, well, convert it to text and then embed the hex in a string in JSON. You don't have to do that kind of thing in CESR. You just say to CESR, okay, this is a cryptographic key or this is a hash, and CESR understands it. The last thing to say at the bottom of these bullets, SAD and SED semantics are changed as part of the document validity checking. So when CESR is looking at a document and parsing it, and it encounters a field that is supposed to hold a SED, if the field doesn't hold a SED for the containing SAD, then CESR complains that the document it's looking at is invalid. So it understands whether the data all hangs together in the same way that a JSON parser would complain about not having quotes at the end of a string or something like that. And that's important. So now that you know a little bit about CESR, let me turn your attention for a second to verifiable credentials. And this will bring us to our final topic, ACDCs. Verifiable credentials, of course, are a way of making claims about particular subjects and then using digital signatures to make your claims verifiable to other parties. And the verifiable credential spec, there was a 1.0 version and now there's a 1.1 version. But there are some fairly widely acknowledged rough edges in the verifiable credential spec. I've listed a few here in red. It's text-oriented and verbose, which makes it a bad fit for IoT and low bandwidth use cases. There's been work to do a CBOR transformation of the data model, and you can certainly get the size down, but that work is not widely adopted and not strongly standardized yet. And even when you try to compress with CBOR, there are still some things about the way the data model works that prevent you from really getting as terse as you'd like. Verifiable credentials reference data outside themselves, the most common example being a schema. So if you generate a driver's license as a verifiable credential, there will be a JSON LD context that is a URL. And in order to understand the driver's license, you have to go fetch the schema document. Now, the verifiable credential is something that you can evaluate cryptographically, but the schema is not something that is guaranteed to be stable. So a hacker who wants to subvert a driver's license could take over the website that publishes the schema and could change the meaning of particular fields. And then software that's parsing the verifiable credential could make different decisions and impute different semantics to the data because the schemer did this attack on the hacker did this attack on the schema. So this creates certain kinds of security gaps. And there have been discussions about this in the community. There's a technique called hash links that can solve this problem, or at least partly solve this problem. And there's general security advice that's given. This is kind of tribal knowledge, though, that basically says, yeah, software that encounters a verifiable credential should only parse credentials that have schemas it recognizes already, rather than going out and downloading schemas of arbitrary types from arbitrary locations because of this problem. The other kind of significant approach to this problem in the space was what was done with AnonCreds and Hyperledger Indy, where Indy basically said, we're not going to let anybody publish a credential until they publish the schema first, and the schema has to be published on a blockchain so that we know that the schema is not changing and doesn't have this vulnerability. Both of those are workarounds that do partially solve the problem, but they're not wonderful workarounds in some ways. And I could say more about those, but we don't have time here. Another issue is that the cryptographic primitives that need to be represented in various parts of the data model don't have well-defined serialization strategies. And so you see conversations saying, hey, let's start up a new effort to standardize how we represent a key, and people saying, but can't we use JWKs? That's a standard way to represent a key and it fits into JSON, and some people like that and some people don't, and they want to do something different and so forth. And what ends up happening is that in practice, although you have the verifiable credential spec, you actually have to reference and pull in numerous other standards to solve this problem. And those standards create interoperability problems. So you have people that are both using verifiable credentials, but they're not using the same serialization of keys strategy, and therefore they're incompatible, even though they're both in harmony with the main spec. And the last two bullets here, the way that statements about subjects are represented is they're conceived of as RDF triples. This is an information theory issue, but basically what it means is that certain kinds of relationships are a little bit awkward to represent in verifiable credentials. A really good example is instead of making a claim that a sensor generated the following value, or that a person has the following characteristic with a probability. So, you know, Alice has COVID with 89% confidence. Instead of representing data like that, you must simply say Alice has COVID, binary statement. Or you can say Alice's COVID score is 89%, but you can't say Alice has COVID where the confidence level of the verb has is 89%. And this leads to some subtle problems in the data model. And lastly, there's no way to model relationships between credentials. And what that means is that if you encounter a credential that says Fred graduated from Harvard, that's great. But then if you say, well, how do I know if Harvard was accredited? That question can't be answered in a standard way. You have to invent some mechanism where you say, oh, well, go challenge the issuer of Fred's credential to produce an accreditation credential. And there's no well-defined way to do that, although there's several attempts to plug that gap. So these are all what I'd call rough edges in verifiable credential spec. So if I take that list of rough edges then and reference back what I said at the beginning of this presentation about SADs and SEDs and so forth, and CESR, let's see what we can do about this list of rough edges. So first of all, what if instead of being verbose and text-oriented, we used CESR to represent the data structures in a verifiable credential so that we could get the terseness of binary and yet still have the flexibility and human friendliness of text? That would be nice. How about instead of hyperlinking to data, we use the semantics of SEDs and SADs to create relationships to things like schemas. This would allow a credential to be tamper-proof, but we wouldn't have to store it on a blockchain, and we wouldn't have to publish schemas on a website in a way that requires us to do something heroic to secure the website. We can simply publish it on the website and know that it hasn't been tampered with because the schema is self-addressing data. What if instead of serializing hashes and keys using random strategies that we invent that sit on top of our spec, if we simply said, let's use a serialization that recognizes those as primitive data types? They're very efficient to represent, and nothing needs to be standardized on top of it. What if instead of using RDF triples, we use something that is a very close cousin? It just has one subtle difference. We represent relationships between subjects and properties using property graphs. And because we're using property graphs, we get for free the ability to build more sophisticated graphs. And that allows us to resolve the bottom thing in a clever way. We say, well, let's use SADs to link to other credentials. SEDs, excuse me, to link to other credentials that are SADs. And this would allow the credential that Fred has from Harvard to contain a SED of a credential from Harvard's accreditation credential and so forth. And now you can chain backwards through credentials to get to a root of trust very efficiently. And you know that as you follow the chain, nothing's been tampered with. So if we did all of these things, what we would end up with is authentic chained data containers. And they have the following benefits: that you can mix and match text and binary inside the credentials, or you can transform a credential from its text to its binary representation transparently. So you can inspect it in a debugger for a developer, but transmit over the wire a binary version of the credential, things like that. And as you do that transformation, you're not altering the hash of the data. You get the terseness, and it comes from several things, not just from one. So unlike CBOR as a representation of verifiable credential, which only gives you the terseness of binary, this strategy gives you terseness from three things: the binariness, the SED-based references, and the fact that cryptographic elements are primitives in the serialization. We get chains of trust with other ACDCs. We get the fact that this is highly cacheable in a really efficient way because of the SAD-SED relationship. If I have seen a credential before, like the credential that accredits Harvard, I know that I've seen it before because I have an identifier for it. It's the SED for that credential. And I never need to go fetch it again. If somebody else refers to that SED, I know that if I did fetch it, I would see exactly the same data that I already have cached. There's no versioning issue here. If it's the same SED, it's the same data. End of story. We achieve all this without having any blockchain dependency at all. And authentic chained data containers are currently a target for an IETF RFC. There is a draft RFC that's been written for them. And these are influencing and perhaps may ultimately be represented fully in the W3C Verifiable Credential 2.0 work, which is just starting up.